In this highlight video, we're going to examine molecular relationships. So after you've watched this video, you should be able to compare any two molecules and determine what the relationship is between them. One type of relationship that we'll look at are isomeric relationships, but the molecules could be the same. They could be non-isomeric relationships. Let's start by reviewing the different types of isomers. So remember, isomers are different molecules, but they have the same molecular formula. There are two general classes of isomers. If the difference in the molecules is in their connectivity, if the atoms are connected in a different way, they are called constitutional isomers or sometimes structural isomers. If the isomers have the same connectivity but they differ in the three-dimensional arrangement of the atoms, then they're called stereoisomers. If stereoisomers are mirror images of one another, they're called enantiomers. And if those stereoisomers are not mirror images of one another, then we call them diastereomers. Let's compare some molecules. In each of these sets or pairs, we are going to classify them as either being the same, different but not isomers, constitutional isomers, enantiomers, or diastereomers. Let's look at the first two. The first thing to do is to determine whether those two molecules have the same molecular formula. If they don't have the same molecular formula, they can't be isomers, and they would be, number two, they would be different but not isomers. So what do you think? Those two have the same molecular formula. We could write that here, same molecular formula. Do they have a stereogenic center? Yes, they both have a stereogenic center. So we need to determine whether they're either the same or enantiomers. They aren't constitutional isomers, and they can't be diastereomers unless they have more than one stereogenic center. So we can go about this in two different ways. We can either determine R or S for the two stereogenic centers. If they're the same, then they're going to be the same molecules. If the R and S are different, then they would be enantiomers. Or we can manipulate one of the molecules to try to make it superimpose with the other. So let's do strategy number 2 first. So it will help if we add in the missing hydrogen on the stereogenic center. So there's an H here, and there's an H here. And so what I'm going to do is I'm going to rotate around this bond. I'm going to twirl that end group like a propeller, and we're going to rotate the nitrogen so it's up at the top. So we rotate this. We're going to get it like this, NH2. So it's gone from the back up to the top. The methyl group will go from the top down in front. And the H will go from the front to the back. All right, so these two are the same. So let's compare here. So the nitrogen's amine is in the same position, but look, the methyl and the H are opposite. So they have the opposite chirality, and so these two are enantiomers. All right, let's go back to the second way. So let's prioritize the groups around the stereogenic center on the molecule on the left. So the nitrogen would be 1, the ethyl group is 2, the methyl group is 3, hydrogen is 4, number 4 is in front. So we can use our shortcut. We go from 1 to 2, 2 to 3, 3 back to 1. This is going clockwise, which would normally be R, but it's not R, it's going to be S. We'll say because number 4 in front. Okay, so this is S. All right, let's do it on the molecule on the right. Okay, so again, we have number 1, number 2 for the ethyl, 3 for methyl, 4 for H. Number 4 is still in front. Okay, so we go 1, 2, 2, 3, 3 to 1. And so this is going counterclockwise. Right, which should be S, but it's not S, it's R, because number 4 in front. Okay, so this is R. So notice one of these molecules is S, one is R. That supports our answer that they are enantiomers. All right, let's look at the next two. Do they have stereogenic centers? Yes, these molecules both have 2 stereogenic centers. In fact, if I look at those two, it looks like we could slide this one right across and they'd be lined up just like mirror images. Okay? But the question is, are they the same or are they different? Same or different? Well, in fact, in this case, I could just rotate this molecule in the plane around like this, slide it right over, they'd be superimposable, and so these are, in fact, the same. Are these molecules chiral? No, they're not chiral. This is like an example we saw before, has a plane of symmetry right down the middle, and so this molecule is meso. All right, what about the bottom one? Okay, they have the same molecular formula. What about connectivity? They have the same connectivity, right? There's a chlorine, OH, chlorine, chlorine, OH, chlorine. Okay, same connectivity, so they're not constitutional isomers. Let's look. We have a wedge for the OH and a wedge for the chlorine on the right, so those two look the same. But these two look opposite. Okay, so we have a situation where we have multiple stereogenic centers. Some match and some do not match, and that is the recipe for diastereomers. Right, so we have some stereogenic centers match. Some don't. So they're diastereomers. Remember, diastereomers are stereoisomers that are not mirror images. Let's try 3 more pairs. Look at the top 2. Do they have the same molecular formula? Yep, they both have 4 carbons. They have 2 bromines. Same molecular formula. So we have, do we have chirality centers? Yeah, or stereogenic centers? Yes. We have 2 stereogenic centers. So in this case, we really have 3 possibilities. They could either be the same, they could be enantiomers, or they could be diastereomers. All right, so we either have to figure out R and S for the different centers, or we can manipulate one structure and try to get it so it can overlap the other. And so that's what I'm going to do in this case again. I'm going to rotate around this center bond, and I want to rotate this methyl group 180 degrees so it ends up in the plane down here. Okay, so I'm going to have to rotate it over here. So the methyl group should be down in the plane. I'll just keep this bromine here. Methyl's there. The bromine is back, so when it goes 180 degrees, it's going to be forward. Right? The H is forward, so it's going to be back. We don't really even need to draw that one in. Let's compare these two, and they are the same. All right? Next two, same molecular formula, but it has no stereogenic centers, right? There's no chirality. So these could either be constitutional isomers or they could be the same. So it looks like here we have, this is called an ester, and this is a carboxylic acid. Okay, so these are constitutional isomers. Because they have the same molecular formula, but they have a different connectivity of the atoms. All right, one last problem. Okay, these structures look like they have the same molecular formula and the same connectivity. All the groups are in the same place. But notice each of the chiral centers, this methyl group here is pointing up, this one's back. The OH is pointing up, this one's back. This isopropyl group is back, this one is up. All stereogenic centers are reversed. So this is what we see when we have enantiomers. So these molecules are, in fact, if we repositioned one of them, these would be mirror images of one another. All right, so comparing molecules like this can sometimes be challenging because it's difficult to rotate molecules around and envision what they would look like from a different direction. So practice this kind of problem. If you have a hard time, use a set of molecular models and rotate bonds and practice drawing the molecule and then checking it with your models so you can get to do it without the models.